Hey guys, so in today's video, I'm going to be delving into the difference between a program and a process. I'm also going to talk about how they coexist in memory. And finally, I'm going to talk about the various states processes go through. So, first of all, let's talk about the difference between a program and a process. So, a program is the code that you wrote. So, it's just the executable code, but it's not running, it's just sitting there on your disk. So nothing's happening to it. It's just text that's sitting there on your disk. Now, once your program moves to memory, which is your main memory, which is also known as RAM, that's when your program becomes a process. So, program is on a disk, not running. Process is in memory, which means it is now running. So, what exactly happens once a process is running or loaded into memory, basically? So when a process is created and it's loaded into memory, it's allocated its own unique address space. And this address space is basically a section of memory that's dedicated exclusively to the process. So basically, when you start off on the disk as a program, and when you move into memory, you become a process. And the memory gives you your specific address, and it gives you a space in the memory. So it's basically like buying a house. So let's say you buy a house. Once you buy a house, you get the space for the house, and you also get an address that, you know, tells whatever the city, whatever where your house is. It's the exact same thing. And just like a house that has different rooms in it that are used for different purposes, um a process in memory in its address space has different sections that hold different kinds of information. So the first section we can talk about or we can think about is basically the code or the text segment. And this is where the compiled program code resides. It basically contains the instructions that the CPU is eventually going to execute. Essentially, it's just like the text of your program. And this segment is, usually marked as read only to prevent the program from accidentally modifying its instructions. Now, next, we have something called the data section. And this section contains, global and static variables. So global variables are basically like the ones, that are used throughout your whole program. They stay there until the end of your program. They're accessible by, different functions, whatever of your program. And static variables, no matter if they're in your function or they're initialized like outside of your function in a global state, they all reside in the data section. So the next section we can talk about is the heap area, and the heap is used for dynamic memory allocation. So when your program runs and it needs to allocate memory at runtime, so for example, when you use the malloc function or the new operator in Java, or you create a list in Python, all of this memory is allocated from the heap. And the heap grows dynamically as more memory is allocated, and it shrinks when memory is freed. That's why there's the empty space that you see above the heap. And finally, we have the stack. So the stack section is used for managing function calls and local variables. It's basically where, short-term data is stored. So when a function is called, a stack frame is created on the stack. And this frame contains the function's parameters, its local variables, and the return address. Once the function execution completes, the stack frame is popped off the stack. So that means that the stack can also grow and shrink just like the heap can. And it also uses the empty space that you see below it. So the heap and the stack use this shared space that is allocated inside their address space, and they can grow and shrink into it or out of it. And each of these sections basically play like an important role in the process of execution. And together they form like the complete address space of a process. And now we're going to talk about the life cycle of a process in an operating system. We're going to focus on the five primary states, which are new, ready, running, waiting, and terminated. And understanding these five states is really important for understanding how an operating system manages multiple processes efficiently. So, the journey of a process begins in the new state. This is when a process is being created, but it's not yet been admitted to the pool of processes that can be executed by the OS. It's essentially the process's birth phase. And here the OS performs various initializations, allocating identifiers, and setting up the necessary process control blocks or PCBs, which are crucial for managing the processes. Next, we move on to the ready state. Once the initialization is complete, the process transitions to the ready state. And that's where the process is loaded into main memory and is prepared to run, but is waiting for the CPU to assign it processor time. This is usually what we call process scheduling. Multiple processes can be in the ready state. There's a queue that allows multiple processes to be in the ready state simultaneously. They're queued up and they're waiting their turn to be executed. The scheduling algorithm of the OS decides which process in the ready queue will be executed next. After that, we go to the running state. So when a process is selected by the scheduler and given CPU time, it moves into the running state. In this state, the process's instructions are being executed by the processor, and the process will remain in the running state until it either completes its execution, so until the program ended, or it requires some IO operations, or it gets interrupted by an interrupt. Next, we have the waiting or blocked state. If a process in the running state needs to perform an IO operation, such as reading from a disk or waiting for user input, it transitions to the waiting state. During this time, the process cannot proceed until the IO operation is completed. It's effectively on hold, freeing the CPU to execute other processes. Once the IO operation is complete, the process moves back to the ready state where it's waiting for its turn for the CPU time. So it once it's in waiting, it goes back to the ready state. It doesn't go back to running. It goes back to the ready state, back in the queue, waiting for its turn to be run by the CPU. And finally, a process reaches the terminated state once it's finished executing its code and performing its task. In this state, the OS performs cleanup activities, reclaiming any memory, any resources that were allocated to the process. And once these resources are reclaimed and is completely done, the process is removed from the system. So, in short, these five states, which are new, ready, running, waiting, and terminated, represent the life cycle of a process. And this life cycle basically allows the OS to manage process execution efficiently, making sure that the system resources are utilized effectively and that multiple processes can run concurrently without interference.